All right, so we're gonna start with this problem, B. Now for this one, just by looking at it, right? Which test would you apply? So we want to know if the series converges absolutely, conditionally, or diverges, right? So by looking at it, I think I'm going to go with the ratio test. Would you guys agree? Because I see a lot of powers, right? So I'm going to go with the ratio test. Okay, so let's work it out. So we're going to see what happens if you take the limit as n approaches infinity of the absolute value of a sub n plus 1 over a sub n, right? So I'm going to substitute n plus 1 everywhere there is n in our formula of a sub n. So this is the limit as n approaches infinity of, so if you substitute n plus 1 into n, so this one, and this one, and this one, we're plugging in n, you'll have n plus 1 squared times 3 to the n plus 1 times ln of n plus 1 plus 2, so that'll be n plus 3, all over 2 to the power of 2 times n plus 1 plus 2. So that's the n plus 1 term. Now I'm going to multiply by the reciprocal of a sub n. That would be 2 to the power of 2n plus 2 over n squared times 3 to the n times ln of n plus 2. Let me know if anyone has any questions so far. Okay, moving on. So now a lot of simplification before you take the limit, right? So check this out. So I'm going to simplify it as I'm going along. So this one right here, I'm going to rewrite it this way. So it'll be 3 to the n times 3 to the 1. That'll be 3 to the n plus 1. Now here in the denominator, I'm also going to rewrite that. So that can be rewritten as 2 to the 2n plus 4, which is same thing as 2 to the 2n times 2 to the 4, right? So I think I did that right, just double check. And then here in this one, I'm going to write this as 2 to the 2n times 2 to the 2. Good so far, right? Okay, now let's cancel terms. So this one will cancel with that, and then this one will cancel with that. Here I can simplify the exponents, right? So this will cancel, which will leave me with 2 to the second power here. Okay, looks good. Now this would give us what? The limit as n approaches infinity of n plus 1 squared times 3 times ln of n plus 3 all over 2 to the second power. That will be 4 times n squared times ln of n plus 2. Okay. Now, can we take the limit? If you take the limit, what would you have? Well, look at the highest power. Here, the highest power would be n squared, right? And then here, the highest power is also n squared. So if you have same degree top and bottom, what is the limit as n goes to infinity? It's the leading coefficient, right? I think someone said something. Sorry, I cut you off.
Oh, that was me, Professor. I said 1.
One, right. Well, in this case, it'll be their leading coefficient, which is 3 over 4. Good. Hey, Marvin, good to see you again. So this would be 3 over 4. Now, will that be less than 1? Yeah, right? It's less than 1. Check. So therefore, this series converges absolutely. So this converges by ratio test. Any questions how I got this answer? Okay. Well, any other questions? So look at it. Let me know if you have any question. I'll give you a couple of seconds to stare at this. So I'm going to do what Marvin says to distribute this first, okay? So we have the integral from 0 to 1. This would be t minus t squared sine of pi t dt. Now here, I'm not going to separate it into two separate integrals. I'm going to go ahead and apply the tabular method from here. So check this out. So you're going to make a column for differentiation, right? So here's, you're going to differentiate. Sorry, I'm going to have a little discontinuity here. Ignore that. And then here's the part that we're going to integrate. So we'll pick the polynomial to be the function we're going to differentiate and the trig function for the integral column. So here I will have t minus t squared, and here I will have sine pi t. And now you differentiate the first column, the first function you chose, until you get 0. So when I differentiate t minus t squared, I'll get 1 minus 2t. When I differentiate it again, I get -2. When I differentiate -2, I get 0. And that's where you stop. Now the second column, we're going to integrate, right? What's the integral of sine pi t? Well, it will be negative cosine, right? Pi t over pi. And then you integrate that again, so you'll have negative sine pi t over pi squared. Let's double check if this is right. Yeah, and then you integrate one more time until you get to this level. So what will be the integral of sine pi t over pi squared? You get cosine pi t over pi cubed. Let's double check that. Now you can double check the second column by keep differentiating, right, this way, and make sure you get the function above. So look at this, stare at it, let me know if you agree with this. I think it looks good, right? Just someone let me know if you see something weird. So now you're going to multiply this with that times +1, multiply this with that times a -1, multiply this with that times a +1. And that's how you get the integration of this function we're given. So what we're going to have is t minus t squared times negative cosine of pi t over pi. Then the second arrow gives us negative 1 minus 2t times sine pi t over pi squared. And then the last arrow gives us negative times positive, that's negative 2 cosine of pi t over pi cubed. And you're going to evaluate all of these from 0 to 1.
Isn't the second term positive because it's a negative of a negative?
Yes, you are right. Thank you.
You're welcome. Thank you.
Good catch. All right, so everything else is okay? Looks good, right? All right, so I hope I didn't leave a negative behind, but please pick it up if you find it. All right, now the rest, we just plug in the upper limit minus the lower limit of integration, right? Let me know if anyone has any question up to this point. So here I use the tabular method to save some time, because if you try to do directly integration by parts, you will end up doing it probably 3 or 4 times. Marvin, let me know if you got something similar since you tried it.
Yeah, I got the same thing.
Okay, great. So let's plug in the upper limit, right? So we have plug in 1 into every t. When you plug in 1 in here, it's going to go to 0. So the first term disappears. The second term, when you plug in 1, you'll have 1 minus 2 times sine of pi times 1. That will just be sine of pi over pi squared. Minus 2 times cosine of pi times 1 over pi cubed. Minus now the lower limit of integration. So I plug in 0 everywhere. So that means this will go to 0. The second term, again, you will have 2 times 0, that will disappear. So it will just be sine of pi times 0. Well, that will disappear too, so that will go to 0. Minus 2 times cosine of 0 over pi cubed. So that's what you get when you plug in the lower limit of integration. And a lot of these will go to 0. For example, this one will go to 0. This one will also go to 0. And then to the only one that survives is this one right here. So this is -2 cosine of pi over pi cubed. Here I distribute the negative out, so that'll be a +2. Cosine of 0 is 1, so it'll be 1 over pi cubed. Now, this one right here, we also know this value, right? Cosine of pi, that's -1, so -2 times -1, that's a +2 over pi cubed plus 2 over pi cubed, which leaves us with 4 over pi cubed. So that will be the answer to this definite integral. Let me know if anyone has any questions. Okay, so let u represent e to the x. So that means du will be e to the x dx. And that's exactly what you have here. That's why it works. So I wouldn't go with any other method than u sub. So if I do that, well, this now becomes the integral. Ignore the limit of integration because they belong to x. You'll have du over the square root of 1 minus u squared, right? Because u is e to the x. Now, what do you guys think? What is this integral?
Is it sine inverse?
You got it. Good job. So this is equal to sine inverse of u, right? And now I plug in u and I bring back my limit of integration. So this would be sine inverse of e to the x going from 1 to 2. There we go. And then plug in the upper limit of integration and lower limit of integration. Now, let me know if this makes sense. Let me know if you want me to explain anything one more time or if it's good. Okay, so let's go ahead and plug in the upper limit of our integration. This would be sine inverse of e to the 2 minus sine inverse of e to the 1. I'll leave it here. This is a good answer, so you can leave it right there. Any questions on this problem?
For the beginning of the equation, doesn't e to the x become u instead of du?
So this right here, this is replaced with u, and this is replaced with du. So when you're rewriting the integral, you're writing it like this. This is the integral of e to the x dx over the integral of 1 minus e to the x squared. So I'm reserving this piece for du, and I'm replacing this with u, my selection of u, and it works.
Okay, thank you. I see it now.
Sure. Any other question on this problem? So the key was to really realize it's a square root of 1 minus something squared, which is a sine inverse, right? Once you're able to realize that, then just, u sub works. So that's why I think this is best done by using u sub rather trig sub. I'm curious how you would go with trig sub though, but somebody work it out and tell me later. Maybe not now, later. So somebody put on the chat if I could just go over all the techniques of integration. Sure, I can go over them quickly. So let's remember what we did in September, right? August, September. Right, so we start in August. You should never forget u sub, right? always go with U sub first, because if you could do it by U sub, there's no need to apply any other technique. And then we learn integration by parts. Right, so you can do that if you have product of two functions that you know how to integrate or differentiate. So the detail is in our class notes. If you want to look over, when do we use integration by parts? When you use integration by parts, there's this this acronym we use, LIATE, for selecting U. So L means, do you guys know what this means? I don't know if you guys saw this or if I mentioned it in class. I can't remember at the moment.
Logarithms, inverse, algebra, trigonometry, and exponential.
Yeah, so if you have those functions, pick those to be your U, and then dv is the remaining piece of the integrand. So this is for selecting U. So the formula for integration by parts is uv minus the integral of v du, where your integral, you're selecting u and dv. That's the formula for integration by parts. Another way to remember this is to just use the tabular method, or you can use tabular method if you want to use the shortcut, so you don't have to remember this formula, but you are in reality using this formula, uv minus the integral of v du. Then another technique that we encounter in this course was, so we had trigonometric integrals. Where you have powers with trig functions like sine squared times maybe cosine cubed, or one of them has odd power, even power, or secant and tangent, they have odd or even powers, something like that. So we talked about how to deal with those. Useful identities to know are these ones. If you have sine square x plus cosine square x, we know that's equal to 1. That's one of the useful identity. Then for tangent and secant, you have 1 plus tangent square x is equal to secant square x. These two identities are often very useful when you're doing a trigonometric integrals. And then we have trig sub. So for trig sub, we have 3 different cases, right? Do you guys remember? So someone tell me one of the case for trig sub. So what if I have a form like this? Let's say I forgot what did I write. Sorry, I could be a little off with notation. So if I have, let's say, some a minus x squared, what substitution would you use? A squared. I think it was a squared. Okay, I remember now. Do you guys remember what substitution we had to use?
That would
A
be
sine
fine.
theta.
So a sine theta.
So you use x equals a sine theta, and then you draw the triangle and you carry on, right? Another substitution we have is if you have x squared minus a squared. If you have that form, which substitution do you use?
X is equal to a secant theta.
Good. And one more form we can encounter. If you have a square root of some x squared plus a squared, or a squared plus x squared, what do we use?
A tan theta.
Good. All right, and then you just follow, okay? So we got to that, and then we talked about partial fraction decomposition. So for partial fraction, sometime you end up doing long division. When do you do long division?
Isn't it when the degree of the numerator is, wait, no.
You're on the right
It's
track.
either greater or equals than the denominator.
Exactly, when it's improper, right? So let's say you're given, I don't know, some integral, let's make it up, make it abstract, okay? So you have some p of x over q of x, right? Polynomials. And if the degree of p is greater or equal to the degree of q, which is the bottom polynomial, then use long division first. Always, sorry, keep going to the wrong page. Long division first. And then you decompose, set it up. Set up your partial fraction, and integration is usually very simple. Most of them turn out to be logarithms, but sometimes don't assume that, right? It really depends on the question. But the key is if the degrees are, the top is greater or equal to the bottom, use long division and then proceed. After that, what did we do after that? So use of integration by parts.
Trapezoidal rules, something. No.
So those are approximation.
Oh,
I think these are all of them.
Would the hyperbolic function count?
Yeah, those are memory. Those are from memory, but they're not techniques, right? They're just different type of functions. So you should know your integral for sine hyperbolic, cosine hyperbolic, tangent hyperbolic, the other three as well.
Partial fraction.
Partial fractions, right? So that's right here. This one.
I'm going crazy, my bad.
It's okay. I think that's the last one, right? I don't remember anything right now, but please look into the notes if I'm missing something. But this is what I can think of at the moment. Integration by parts, trig integral, trig sub, partial fractions. Yeah, that's it. I can't think of anything else. All right. Leonor, let me know if you have any questions or if this is okay. Sorry, that was Anthony. I'm sorry. Confusing.
Professor, I have a question.
Mm-hmm.
It's actually from the second test. It's just I don't remember how to do this. It was like determining the sequence of n minus 5 over n to the nth power if it converges or diverges, and the answer was like e to the negative 5.
Which question is it?
Number 2.
Oh, number 2 right here.
Yes.
So well, the solution is here. Does this make sense?
I just didn't know. I just forgot how to get there a long time ago.
So this one we often just memorize. This is from Calc 1. So if you have so I don't know if you guys saw this in Calculus 1. You should have seen it. If you have, so let me copy it from here. Okay, so here's the question. So what I did, I rewrote the inside, right, of the sequence. So let me know if this makes sense. I just separated them, right?
Yes.
So now here you are trying to remember this from Calculus 1, that if you have a limit as n approaches infinity of, let's say 1 plus x over, let's say 1 over n, then this limit is e. Let me know if you remember that from Calc 1.
Oh, yeah, I do. Yep.
So what we did here is so I don't know if I show all the work. Let me see. Oh yeah, I did show all the work here. So yeah, you can go through the detail, but I'm just going to explain from here that if you, instead of having 1 here, we have a negative 5. So if this limit is 1, then this limit will simply just be e to the negative 5. So just using that logic from Calculus 1. But if you were to see all the work, how this is done, then I used the L'Hopital's rule right here. And I took the limit of the right-hand side. And that's how you got the negative 5 from. So that's just e to the negative 5.
I get it now.
You got it? Okay.
Thank you. But I also had another question. It's
Mhm.
actually not a question. It's not a problem. It's you know, when you have an integral and the bounds are like the same bound, like pi to negative pi. So if
Mhm.
it's an odd function, the answer would be 0. But if
Right.
it's an even function, what do you do? Like you change the bound, you do something with the bound, which I don't remember. I couldn't find it online either.
So here's what you're gonna do. If you have, let's say from, so let's take a look at negative pi to pi of cosine. So if you're integrating from negative pi to pi of cosine of x, now cosine is an even function, right? And the
Yes.
interval is symmetric. So that means you can do 2 times the integral from 0 to pi of cosine of x dx. So you can double the integral and just go from 0 to pi.
Oh.
So for even function, we do that. For odd function, it's going to be 0.
Let's say if it's not a symmetry, so you just do negative infinity to 0 and then 0 to infinity, right? Or whatever the bound is.
Well, whatever the bound is. Only if it's symmetric, then you can use the odd and even function properties.
Right. Thank you.
So the even function will double the area, or the odd function will just cancel each other out. Okay. All right, good. Anyone else have any other questions? Let me see what's in the chat. So number 8 from the department final, the sample. So let's go back here, number 8. All right, here's number 8. Oh, did you want it A or B? I didn't realize it has 2 parts.
A.
A, okay. So let's do A. So I'll let everyone think about this if you haven't done it yet. And then I'll show you how I would do it. To find the interval of convergence of this power series. Now, every time you have a question like this, which test do you apply?
Ratio.
Ratio.
So let's do it, right? Use the ratio test. So we are going to take the limit as n approaches infinity, absolute value of, so plugging n plus 1 with every n. So you have n plus 1 times x plus 1 to the power n plus 1 over 5 to the power n plus 1 times the square root of n plus 1 squared plus 4 times the reciprocal of a sub n. So that would be 5 to the n times the square root of n squared plus 4 over n times x plus 1 to the n, everything in absolute value. Now simplify, right? So as always, you rewrite all the exponent. I'm going to rewrite this one. So that would be 5 to the n times 5 to the 1. And then I'm also going to rewrite this one right here, because x plus 1 gets a power of n1. So you'll have x to the power of n times x plus 1 to the 1 power. And now we can simplify, right? So now I can cancel 5 to the n with 5 to the n, x plus 1 to the n over x plus 1 to the n. And that's it, right? So now all of this will just be the limit as n approaches infinity of n plus 1 times x plus 1 times the square root of n squared plus 4 all over 5 times n times the square root of n plus 1 squared plus 4. All right, let me know if I missed something. I think this is okay. All right, now let's separate the x and n. Now, since n is going to infinity, you can drop the absolute value for the n's. So you'll have the limit as n goes to infinity of n plus 1 times the square root of n squared plus 4 all over 5n times the square root of n plus 1 squared plus 4 times the absolute value of x plus 1. So I'm keeping the absolute value with x, and everything else I removed the absolute value. Now, if you take the limit, what is this limit right here? Well, what's the degree on the numerator?
Is it 2?
Well, so this one will simplify to 1, and then this is a 1, so it'll be a 2, right? And then here is also the same thing, right? So they have same degree top and bottom, which means the limit as n goes to infinity will be the leading coefficient, which is 1 over 5 times absolute value of x plus 1. Let me know if this makes sense. Now I want this to converge, right? So we want to make sure this is less than 1. And then you solve for the interval of convergence. Multiply both sides by 5. So you have absolute value of x plus 1 is less than 5. Now split this up. So you have x plus 1 is between -5 and 5. And if you solve for x, x is between -6 and 4. So that's the interval of convergence, but we have to test the endpoints, right? Well, let me know if you have any questions so far. All right, so further then let me know if this makes sense. You got it now, right?
Yeah, I got it.
Okay, so let's test the endpoints, right? We plug that into the original. So I'm just gonna copy the original to the bottom and see if this series converges at the endpoints. All right, so that's the series we're looking at. So at x equal -6, if you plug in -6 into this x right here, you will have the sum from 0 to infinity of n times -6 plus 1, -5 to the n, right? Then I can pull out the -1 to the n and then 5 to the n, all over 5 to the n times the square root of n squared plus 4. Now, if you simplify this series, you'll have the sum from n goes from 0 to infinity of -1 to the n times n over 5 to the n will cancel out square root of n squared plus 4. Now tell me about this series. What do you know about this series? Converges or diverges? What do you guys think?
Does it converge?
Converge? How do you know that?
So you can rewrite the square root, right? And then
I think it's gonna diverge.
Yeah, can't you do the n term plus here? Because the denominator n squared, if you simplify, would have n over n is of 1, and so the n term divergence test
Exactly.
works.
You could do that too, or you could do the limit comparison. Everything will give you divergent. So this diverges. Good. Right, you could also compare it to a p integral and then do the limit comparison. So this endpoint, we have a divergent series. Now, what about at the x equals 4 at this endpoint? We have the sum from 0 to infinity of n times. Now plug in 4, you'll have 5 to the n over 5 to the n times the square root of n squared plus 4. Again, 5 to the n will cancel, right? You have the sum starting from n equals 0 to infinity of n over a square root of n squared plus 4. Now again, same argument, right? This will diverge. This diverges. So therefore, our interval of convergence, it's going to be open, -6 to 4, open. That will be the interval of convergence. So there is no convergence at the endpoints. They have to be open. All right, let me know if anyone has any questions on this.
Yeah, I
You
have a
wouldn't be
que-
able, oh, sorry.
oh, sorry, you could go ahead.
Go Marvin, is right, sorry.
All right, so on the final tomorrow, they're not gonna ask us whether it converges conditionally, right? Or,
Not at the
That's-
endpoint.
oh, okay.
Yeah. At the endpoint, we just want to do it like this and see if it converges or not. And that's good enough.
Do we have to test for conditional and absolute convergence?
Oh, not for this question. For this question, you just want to know the interval of convergence and if there's any convergence at the endpoint.
Right, like when you're testing for the endpoint, if it's like conditionally convergent,
That's not important.
so you don't need to know that?
No, not at the endpoint.
All right, thank you.
I know our textbook does that, but on the final, we don't really test for that particular, very specific convergence at the endpoint.
So you just test for absolute convergence if it's an alternating series? Like for x equals -6?
For this type, yes, you just look for if it converges at the endpoint or not. That's it.
Okay.
That's good enough.
All right, thank you.
All right, any other questions or any question on this problem? Okay, so it's improper at 2, so that means we're looking at the integral from 0 to 2 of x over x minus 2 dx plus the integral from 2 to 5 of x over x minus 2 dx. Now only work with one of the piece, and if it diverges, then you don't need to waste time working on the other piece. So which one do you guys want to do? Doesn't really matter, right? I'm gonna go with this piece. Since it has 0 on the bottom, I like that, so I'm gonna go with that. So I'm looking at the intervals. I like to draw this. It gives me a better view from 0 to 2, and I'm coming to 2 from this direction, so from the left. So we'll translate this into a limit as some b approaches 2 from the left because it's improper at 2. And we're going to integrate from 0 to b of x over x minus 2 dx. Now I like what Shameli said. She said, let's add and subtract 2 at the same time from the numerator. So it looks exactly like the denominator. Now, sometimes we use different techniques to integrate, but it's not really, it's something you learn to do, but it will just come to you. So I'm going to rewrite this as the integral from 0 to b of x minus 2 plus 2 over x minus 2. Let me know if you guys are okay with that. Do you see what I just did? So I did that, right? I added 2 and subtracted 2 at the same time. And now I'm going to separate this in the following way. So this is equal to the limit as b approaches 2 from the left of the integral from 0 to b of 1 over x minus 2 plus 2 over x. Oh, wait, hold on. Sorry. What the heck? Sorry, guys. I messed it up. It should be just 1. And then 2 over x minus 2 dx. Let me know if you guys are okay with that. So I'm separating this. This is x minus 2 over x minus 2 plus 2 over x minus 2. And that's what I got this from. All right, so stop me if you have questions. I'm going to continue. Now I can integrate, right? So we have the limit as b approaches 2 from the left of integral of 1, that's just x, plus, what's the integral of 2 over x minus 2?
2 ln x minus 2.
Good. This is 2 ln absolute value of x minus 2. And we're going to evaluate this from 0 to b. So now this is equal to what? the limit as b approaches 2 from the left of, plug in the upper limit, that's b, plus 2 ln of b minus 2, and then minus, now plug in the lower limit of integration, that would be 0 minus 2 ln of 0 minus 2. All right, now we're ready to take the limit, but let's simplify a little bit more. So this is equal to the limit as b approaches 2 from the left of b plus 2 ln of b minus 2. And then this is just 2 ln of 2, so minus 2 ln of 2. Now those are just numbers, so you can ignore all of these. They're just numbers. Now let's pay attention to this right here. If you plug in 2, you'll have ln of 2 minus 2, right? Which is 0. But take a look at where are we approaching 2. We're approaching 2 from the left, right? So that means you're going to get a number that's close to 2 from the left. So for instance, maybe 1.99, right? So I can approach something like this. So you'll get a negative value. Now, will that be a finite number or an infinity? So if you look at ln, right? So this is going to be a very small number. So ln looks like this. This is 1. Now this input, if I'm getting closer to 2 from the left, I can plug in numbers like 1.999, right? Or 1.998. So that input is going to be ln of very tiny number, maybe 0.001. Very tiny, right? Or 0.01, 0.0111. So that's somewhere right here. So if you look at that number, it's just going to get closer to negative infinity, right? Would you guys agree with that? So therefore, this is actually going to infinity, which means it's divergent. Let me know if that makes sense. Yep. Okay. All right. So Catherine says yes. Anyone else agrees or disagrees?
Wait
It
for the
converge. It will
for-
converge if it goes to a number, right? If I got a number, then it'll be a convergent. Because I got infinity, that means it's divergent. Ramiro, go ahead.
for the top. What happened to the other part? You know how you split it up? Like the second step when you split it up from 0 to 2 and 2 to 5.
So I didn't work on this one. I only work on the first piece, thinking they will diverge so that I don't have to waste time on the other one. So because this piece diverges, then automatically, it doesn't matter if this piece converges, it's going to diverge with the other one. So we can say, yeah. So because of that, we can say this whole thing, it's going to diverge. So in this case, because you're taking the absolute value of that number, we're going to positive infinity. That's why I put positive infinity. But if you're going down, then it will be negative infinity, right? So you can still say diverges.
If the first piece converged, then we have to check if both converges, right?
Exactly. So if I got convergent on the first piece, then I have to continue working on the second piece. All right. Any other questions? Okay, so let's take the absolute value and see if it converges absolutely. So I'm gonna take the limit as, wait a second. So the instruction for this question was, does it converge absolutely, converge conditionally, or it diverges? Okay, so if you do the absolute value test, so you take the limit as n approaches infinity, absolute value of -1 to the n over times n squared over n squared plus ln of n. So the absolute value will throw away the -1 to the n, so there's no alternation anymore. So we're really just looking at the limit as n approaches infinity of this an. Now use everything you have to see if this will converge or diverge. What would happen if you take the limit?
Is it 1?
It's 1. The limit is 1, right? So what can you say?
It diverges.
Diverges by?
The nth term test for divergence.
Exactly. So there you go. Now, if you try to test for conditional convergence, you will still get the limit to be 1. So it doesn't converge conditionally either. Therefore, it diverges. Let me know if this makes sense.
There were,
Oh, sorry,
Go ahead.
go ahead.
no, go ahead. And it's not a question.
I just wanted to make sure that, is it because of, I'm not sure why it converges to 1. Isn't it just basically because of the degrees?
So, right. So this is a very slow function, right? It doesn't matter where you plug in, the numbers are very small. So you're really just comparing n squared with n squared. So we know from calculus 1, if you have same degree top and bottom, the limit is their leading coefficients, right? So you have 1 over 1. That's why the limit is 1. And now we know this diverges because of the nth term divergent test that tells that if the limit is non-zero, right? Then it diverges. So we got a non-zero value, which is 1. Therefore, it diverges by the nth term divergent test.
Okay, Professor, thank you.
Okay. Oh, Shameli, go ahead.
I was just gonna say, when I was doing a lot of problems from the example, I
Mhm.
realized most of it was from your test. It was on the exam. Yeah, that's it.
Yeah, the answers are out there. See, if you either look at the test or the quizzes, you will see these questions are just slight variation to those questions. Yeah. All right, so this will be our last question. So I wish you guys all the best tomorrow. Have fun, study, get a lot of rest, and make sure to have some coffee as well, because it will keep you awake for a while. But tomorrow, not tonight. Maybe tonight you want to rest well. So I will see you guys tomorrow. And again, shoot me an email if you still have any questions. Oh, thank you. Appreciate that.